So the idea was that since this energy is traveling from sun to the earth, there must be some sort of medium. But we also knew that the air doesn't extend all the way to the sun. It's just the earth's environment. So what's in there? We cannot see it. So now, can we detect it, right? So to detect that, to attempt to detect any material, and by the way, that invisible material, what's called ether. So this instrument was designed to actually uh, see or to find out if there is some medium in between Earth and the Sun, okay? And was able to verify that it's nothing there, okay? It could not prove there is something, okay? So anyway, so this one has like 3 meters. These two are like regular mirror, which completely reflects the light. And this is partially coated mirror. That means part of light can pass through this and part of it gets reflected. So both reflection and transmission occurs through this mirror, but only reflection occurs through this. And this is screen and this is light source. Okay, very simple setup. And in actual setup, there is some sort of, uh, the screw setup that you can very gently, you can move one of these meter, okay, to create the path difference so that you can measure the path difference and you look for the interference pattern here. Okay, let's watch a video. It shows you how it works, okay? So what we do is we look for, so we change the position of this mirror slightly, and then we look for how this interference pattern, interference fringe change, okay? So there is bright spot in the middle, for example, and then there is not so bright spot, and then bright spot, not so bright spot, remember? We talked about that kind of pattern, right? So here, it appears as a circular pattern, okay? So there is this video. Let's watch it, okay? So as you can see, there is light source and there are these mirrors.
Laser, mirrors, and beam splitter are mounted on precision kinematic mounts for fine-tuning and alignment. The interference fringes are obtained on a screen and can be viewed with naked eye.
So that's the interference fringe, and you can see the red bright spot and the dark spot. And because of the nature of the setup, it becomes circular, okay? And while doing this experiment, what is done is the position of one mirror is slightly changed, and we're gonna see how many number of these fringes. So for example, we call this bright fringe, this is dark fringe, and this is bright fringe again, right? So when we move mirror, what happens? These fringes seems to be, depending on which way we are moving, it may seem like collapsing or appearing, okay? So we count the number, change in the number of fringes that appears to be, collapsing or appearing. So that's what we count. And we also note down how far the mirror moved total. So with that, it lets us do some awesome calculations.
Students can assemble the interferometer out of individual modules by fixing them on an optical breadboard. Experiments possible with this setup are Determination of wavelength of laser beam. Finding refractive index of transparent material. Studying the refractive index change of air under different pressures, and to determine refractive index of air.
So anyway, so that's how the setup looks like, and that's what we look for, right? And if we want to find refractive index of air, then we put this tube here, and they're going to be air, for example, and light passes through the air versus, through the tube there versus without it. So you compare it, right? Or you can put anything inside it and you can find the refractive index, and you can find the defects in the materials and so on, okay? So if you want to know optical property of any body fluid, you can put that in the container and do the analysis, okay? So here is one example. Let's say the experiment was done, right? And the bright fringes appears on the screen as one of the meter moved by that many meters, okay? So meter moved, you saw that there was that micrometer screw there. So when you turn that, it pushes meter, and it also gives you the reading, okay? And it's in the micrometer range, okay? And there were 92 bright fringes that were counted on the screen, okay? So by the time it was moved through that much distance, what happened? That many fringes either appear to, come up, or disappear. So now the question is, what is the wavelength of the light used in the interferometer? So we can do that. So what happens is we have a setup such a way that, let's say this is beam splitter meter, right? The light passes through the one of the meter that's moving, okay? So what happens? It has to travel this much distance and that much distance, right? So it goes to the meter and comes back from the meter. So it's traveling 2 times the distance. So if we move this meter by d distance, that means what happened? The path of the light, path difference of the light changed by 2 times d. Okay, so that's what it is saying. So path length difference 2d round trip, okay? And the number of these bright fringes, that's 92 in this case, right? So what we can do is, okay, since there are n bright fringes, the extra path, that's going to be equal to the extra path length. And remember, distance between one bright fringe to the next bright fringe is exactly one wavelength, right? So we saw that last class when we are looking at the maximum positions, right? So what happens? When it's in phase here, then after one wavelength, it's going to be also in phase. So that means change in one fringe means the path difference must be equal to the wavelength. So that means if there are n fringes change, means the path difference must be n times lambda in terms of wavelength. And in terms of what we measured, it must be 2 times d, because that's how far the light is moving. So they must be equal. So now from here, we can calculate wavelength, okay? Since we know d here, and we also know n, which is 92, we can get this number. And here we're not changing any unit. It's in micrometer. So the answer also going to be in micrometer. So Let's see. So you can convert that into meters if you like. 1 micrometer is 10 to the power negative 6 meters, right? Just like 1 millimeter is 10 to the power negative 3 meters, or in other words, there are 1,000 millimeter in a meter. Similarly, there are 1 million micrometer in 1 meter, okay? So a meter is a millionth of a micrometer. A micrometer is a millionth of a meter. Okay, so that's what that is, just like this. So you can multiply that and can convert that. Okay, so yeah, so this is one example, but of course it's gonna slightly change when we put some medium in between. Okay, for us, for now, let's just keep on this, like how the change in wavelength or path difference is equivalent to number of fringe changes in this case, okay? So this is nice, one example here. So now let's talk about diffraction. So interference, waves coming from two sources are mixing, superposing, interacting. So that's what's happening, right? And now, for the diffraction, what happens? The waves are not coming from two sources. It's just coming from one tiny, tiny, tiny hole, okay? So that's how it is coming. So that's the difference here, okay, between interference and diffraction. So there is this short video. Let's watch that.
The next thing I want to look at is what happens to a water wave when it passes through an aperture. Well, I fitted an aperture here, but it's rather too wide for it.
So can you guys hear the voice from the computer, sound from the computer, video?
Yes.
Okay, great.
What I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction.
So narrower aperture, more diffraction.
If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this control here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction. If I make the wavelength smaller again, is where we started, an even shorter wavelength, then there's less diffraction. So here are the two separate factors that affect the diffraction of a wave passing through an aperture. The wave spreads out more if the aperture is made narrower, or if the wavelength of the wave is increased. And conversely, it spreads out less with a wider aperture or a shorter wavelength. In fact, all kinds of waves, not just water waves, exhibit diffraction at an aperture, as long as the aperture is not too big.
Okay, so now we saw what happens when wavelength changes. What happens to the diffraction? Is there more diffraction or less diffraction? Similarly, when aperture, the size of the hole changes, what happens to the diffraction? We saw that in that experiment, okay? So now in physics, we want to write the equation that actually tells exactly what we observed. In some cases, we can just write the equation without doing experiment. Okay, we can do that. And then later we can do experiment to see if works out. And it works out beautifully if you did not make any mistake. That's the beauty of physics, okay? So we want to write down the equation so that we can describe the phenomenon we saw. And by the way, yes, it depends on the, opening and wavelength of the light is very small, just like we saw from the Michelson, interferometer. It was about half micrometer, folks. And micrometer, size of micrometer, if you were to pull a strand of your hair, the width of that hair strand is in the order of micrometer. So the wavelength of light is smaller than that. Let's keep that in mind, okay? So that's how small openings you need to observe the diffraction of light. But water can have longer wavelength depending on how you produce the waves, right? And so you can easily see the diffraction phenomenon. Sound has a long wavelength. So because of that, what happens? We can observe the diffraction. So for example, let's say I'm speaking in this room and there is wide opening. The door is about half meter long, right? If a person is sitting on the side of the door, okay, side of the door, far. So door opening is here, right? Door opening is here. And if person is sitting over there, that person can hear the sound. Why? Because sound has a wavelength comparable to the width of the door, opening of the door. So because of that, sound wave diffracts when it passes through the door. But when we shine light through the door, what happens? Light can pass. I'm talking about open door. So light passes and it goes straight. It doesn't spread. It doesn't bend, okay? Unlike sound wave. So that's the proof of the wavelength dependence of the wave. We can see that in our daily life as well. But we don't observe diffraction of light in our daily life because light is not passing through that very small hole, okay? So now, here is an example of the diffraction of light. So this hole here is very small and it's coming through the very small opening, just like water was coming out through the opening, and it wasn't very small because water waves have relatively longer wavelength. You can generate longer wavelength by making that, by changing the frequency of the tapping, you can adjust the wavelength of the water wave. So we had an opening something like this or that. We saw the diffraction going from very pronounced to not so pronounced for the case of water. Here we have similar, let's say, setup. So there is this small opening and it is smaller than what you see here, okay? It's a magnified. And the waves are coming out like this, okay? So they are spreading just like water wave, light waves spread out. And of course, this is not real picture, it is just a sketch, okay? And now if we put screen, if we put a screen and look at the diffraction pattern, what happens? You don't just see one bright spot. So since it is just coming from the one, opening, we call this kind of setup a slit, okay? So it's coming through just one, and we may, think, okay, they're going to be just one big bright spot. If that's the case, when opening is larger than the wavelength of the light. But when opening becomes smaller, what happens is you observe this interesting phenomenon where you see now there is big patch at the center directly, in front of the opening here. The slit is somewhere here, okay? Slit is somewhere here. So that we call central fringe. And then there is not so bright spot, and then bright spot, and again, not so bright spot. So now, another difference you can see, you can tell whether it's a diffraction pattern or interference pattern is by looking at how intensity is changing. So bright spot is really bright. So here, the large peak means large, intensity is higher. And then what happens? No peak at all, zero intensity here. And then there is again a bit, brighter, but it's not as bright as it is at the center. So that's why this peak is smaller, and they get smaller and smaller. But for the interference pattern, for a certain, up to certain, distance from the central spot, the brightness does not change much, okay? It changes a little bit, but not like this, not drastic change. And so that's what we see. Now, let's write down the equation, how it's happening, what's happening, how do we describe it, okay? So the diffraction is also acting like an interference, a kind of special case of interference. There must be mixing of wave going on. Otherwise, we shouldn't be seeing the canceling. See, there is canceling means there is destruction going on. And we learned that that's a destructive interference. So diffraction and interference, they are related. The difference is, in case of interference, the waves from two slits, two sources are meeting at a spot and, combining. But in case of diffraction, what's happening? Wave is just coming out from the one opening, just one opening, one source, okay? That's the difference. So because of that, the interference pattern looks different. The interference pattern looks different. And to differentiate that, we call this phenomenon diffraction. But actually, there is interference going on when we are observing the diffraction, okay? So let's keep that in mind. So it may look kind of very similar when we write the equation. So to describe that, since we know there is interference going on, then what we do is we need to talk in terms of interference from two different places, and there is path difference and so on, right? So we need all those, just like we did for the interference. We need all those, okay? So now what we do is, so when there is a wave, when we started talking about light and we described propagation of light as a wave before we started going to the ray description, okay? The refraction, reflection, before we started talking about reflection and refraction, we talked about Huygens principle, where we said, okay, how light propagates, how do you describe? So in that case, we described in terms of propagation of wave front, right? So you assume, so how do you go from this wave front to another, that wave front? How do you describe that? To describe that, we use, in the Huygens principle, we use this, we said, okay, every point on this wave front acts like a source of light. So now this can, the wave, so it acts like a source means it can produce wave, and these wavelets can move. this wavelet can move, we said, right? So now, similarly, now, although this is just one opening, so when the wavefront is reaching to that opening, we can think of, okay, it is made up of many sources that producing many wavelets, and that's how it is propagating, okay? So we can make that assumption. Now, each dot are the sources here, okay? So that means now the lights are coming from many sources and meeting there. So that means when we are looking at the diffraction pattern somewhere here, what's happening? This is center, right at the, maybe, so it's gonna be, so if I have a screen like this, so this is gonna be center with large brightness, okay, large intensity, and then they're gonna be dark, and then they're gonna be bright, and so on. So they're gonna be these fringes, right? So to describe that, what we're gonna do is we're gonna assume just 2 points. Let's say one point at this on the side, you know, at the side of the opening, and another point at the middle of the opening. And let's assume these are acting like a 2 light sources, and light reaching to the screen. They are interacting with each other, okay? So now what happens? So light, when it reaches here, this one travels this much distance, and light, let's say going from here, travels this much distance. So there is path difference. You see that? There is this path difference, okay? So there is this path difference. We need to figure that out. So that's what this diagram is about. So one that's going from the center and one that's going from the side. So the distance between them gonna be just like we had for the interference, distance between two sources, we said that was D. So in this case, it is half the opening. So if this opening width of that hole is A, then in that case, D gonna be half A, okay? And remember, we have this D sine theta is equal to M times lambda condition, and that's what we are using. So now we can replace D by half A. And the path difference now becomes, the D sine theta becomes half A sine theta, and that's what you see here, okay? Now that is equal to M times lambda, okay? M times lambda, and M are integers, right? So now, so when M was 0, when M was 0 in our case for the interference, there was bright spot, constructive interference, bright spot or constructive interference. And when M was 1, bright spot. But when we had, let's say, you know, for the destructive, we had something like this, lambda over 2, right? Oh, I think it was not lambda over 2, just lambda. So now for M is equal to 0, what happens? This becomes half wavelength. So where does the first dark spot appears? When M is equal to 0. The first dark spot gonna be at M is equal to 0, right? So now that's what we are writing here. First diffraction minimum, dark spot means minimum, bright spot means maximum, brightest point and not so bright point, okay? So we are writing the minimum condition, not the maximum condition here. So why are we doing that? Because we have this factor of half here, and for the minimums, for the diffraction, we have this half coming out for M is equal to 0. So what happens? Now this half and half cancels, leaving this like d sine theta is equal to, let's say, lambda for the first minimum. Or if I write M lambda, then this is gonna be for M is equal to 0. First minimum gonna be for, oh, not that. it has to be m is equal to 1. So for first minimum, I have to write m is equal to 1 because I'm getting a sine theta is lambda, right? So that means m is like a 1 there. So when I compare with this interference equation to this diffraction equation, what's the difference now? The D is not half now, but it is whole opening now. Instead of D, we are doubling that, let's say. Okay, so this is whole thingy. That means what happens? This becomes like lambda. So for the interference, we talked about central maximum, m is equal to 0, and first maximum next to the center, the first in one side, was m is equal to 1. Here, m is equal to 1, gonna be what then? First dark spot, minimum. There is no dark spot at the center. It's a bright spot, right? It's a bright spot. So that's gonna be m is equal to 1. And that's what you see here. M is equal to 1. Okay? And then when you look at the m equal to 2, that's what that is. And that's what that is here. Okay? When you are writing, see this equation here, so a sine theta is m lambda, means m is a sine theta over lambda. So that's what you see here, right? And these are the different m values. And that's how the diffraction pattern look like when you make the intensity plot. Okay? So I hope you notice the difference there between interference and diffraction. For interference, all these are about same. And we say, okay, m is equal to 0 for this, and m is equal to 1 for this bright one. Okay, so that's how we use it. But for the diffraction, what are we doing? We are saying, okay, the first dark is the m equal to 1. Okay, so we need to keep that in mind while using this formula. Otherwise, formula looks exactly same now. Okay, so a sine theta is m lambda. T sine theta is m lambda. What's the difference? This gives you minimum. This one gives you maximum for the interference. Okay, only that's the difference. Otherwise, formula looks similar, so don't get confused. There is difference, so keep that in mind. And there is no m is equal to 0, as you can notice, because there is no central minimum. So let's take a look at this one here to see you know, how these different parameters are related to each other. So there is this slit width, and there is a screen, and there is first minimum, right? And we are saying, okay, that distance of that first minimum is x from this central maximum, okay? So that's what's happening here. If the width of the slit is increased by a factor of 2, so just like we saw in that experiment, when width of the slit was increased, diffraction or the spreading was becoming smaller, right? So now, can we write down that equation based on the information we have now, okay? So can we do that? So that's what it's saying. So if it is increased by a factor of 2, what happens to the width of the central maximum of the screen? So the width of the central maximum, see, it is first minimum, and other side first minimum gonna be something like this, means this is the central maximum, right? So that's the central maximum, width of the central maximum on both sides. So if we look from one side, what happens? This is x. If x increases, that means width is increasing. If x decreases, width is decreasing, right? So we want to relate how this x is related to a. We want to see, okay? That's what we want to see. So since this x is related to theta, we can easily use that equation we had and write that down. Okay, so for m is equal to 1, we can write, like this, and with m is equal to 1, it's going to be just lambda. Okay, so what it means, if the angle is small, for angle is small, sine theta is nearly equal to theta, right? So we can talk in terms of theta. So what happens in this case? You can think of this equation as, approximately a theta is equal to lambda. So a theta, and since x and theta are related, theta increases means the width increases. Theta decreases means this width of this thingy decreases, right? So now, what happens to the theta when a increases? It says what happens when a increases, right? So wavelength of the light is fixed. Okay, so if we are shining a red light has a fixed wavelength, so it's not changing. So this is like a constant. So now again we can go back here and write that's constant. So a times theta is constant. So I always like this equation here. 64 is 8 times 8. So if you increase a, what does that mean? That means, let's say 8 goes to 16, doubles. A doubles, right? A means slit width, doubles. Since this remains 64 or constant, right? It remains 64 means now theta has to be what? It has to decrease by same proportion. So it has to be 4. 16 times 4 is 64. So when a doubles, theta becomes half, right? So that's how they are related. So we can write that relationship. So what does it mean? When it is nice, means the spreading is larger. Just like we saw in that video, when those two, like let's say when the aperture or the opening of the water flow was decreased, the spreading was larger. Theta larger means spreading is larger. That means diffraction, more pronounced diffraction, lot of diffraction. But so theta decreases means not much spreading, means not much pronounced diffraction. So that's how we can describe by using equation. See, we described what we observed, what we saw in the video, okay, using mathematics. So even if we did not have that video, just by using this idea, theory, and little mathematics, we could just tell it. We don't need to watch video anymore, okay? So that's the beauty of physics, okay? So if you want to write in terms of x, you can do that as well. So for example, this theta can also be written as a sine theta is also nearly equal to x over d. So if you want to relate d and x, you can do that just like we did for the interference, okay? Just replace this, replace that by sine theta by x over d and talk about it. Here I'm just talking in terms of theta, okay? And so theta here means this lambda over a, and we can directly see theta and a, they are inversely related. So it's talking about same thing we talked about, okay? So that's that. So now, how do we achieve the diffraction? So opening has to be really small. So for that, what we do is we scratch surface of transparent glass or plastic. So where we scratch, what happens? Light cannot pass through that. And on a scratched surface, it still remains transparent. By doing that, you are making a device called a diffraction grating. Okay, so you scratch here, light is not passing through that. And on a scratched one, light is passing through that, okay? So that's what it's talking about. So now let's suppose the distance between two consecutive scratches. So what does it mean? Let's take a look here. Let's suppose this is 1 centimeter wide. And I drew how many lines here? 1, 2, 3, 4. So let's not count that as a line, right? So what happens here? I'm scratching this. So now this is like this opening here, okay? And this is this another opening. So that's what it is. So you can draw many lines. So actually when you make it, what you do is you draw hundreds of them in 1 centimeter. And remember, 1 centimeter is less than ½ inches. There are 2.54 centimeter in each inch. If you are not, you know, if the centimeter is not coming up in your head, probably you know 1 inch, how much is 1 inch, right? So anyway, so you draw hundreds of lines, even thousands of them, okay? So you have now several openings. Now, how many lines are there? So, for example, if this, let's say, so if this is 1 centimeter, and if I drew like how many lines? 1, 2, 3, 4 lines there. Then what you have is like you have this opening 1, 2, 3, 4 plus 1. Okay. So now let's say that's the distance between the opening. So distance between the opening is related to the number of lines you draw. More lines you draw, the distance between opening becomes smaller, isn't it? So they are inversely related. Number of slits to every centimeter, they are inversely related. More line you draw, what happens? Distance between them become smaller by same proportion. So that's what it means, okay? So they are related like this. And we can use that equation here. Just like we would for the, now for the, for this, see, this is like one opening, this is like another opening, and this is distance between openings. So it's like, it's just like now, interference now, okay? It's just like interference, so that's why we can write this equation for maxima, not for minima, see? So, okay, and so that's how they are related, okay? And we can use this equation for the diffraction grating. Now, we can use this information to figure out like how much detail in an optical instrument can capture, okay? How much details. So for example, let's say we are trying to see if there are like 2 cells in a membrane. In a membrane, let's say how many cells are there? We are trying to look at it, right? So this is 1 cell, let's say 1 cell, and this is nucleus, this is another nucleus, right? So that's the separation distance between the cells. So now, if our device, optical device, has a resolution large enough, in that case, we should be able to tell, oh, there is 1 cell there, there is another cell, okay? But if it's not, the resolution is not enough, then what's gonna happen? It's gonna be just blurry bulb, blurry block, okay? And you cannot tell if there are 2 or just it is 1, okay? So if you wanna see the fine details, that means you need high resolution. So how the capacity of an instrument is limited, that depends on different factors. For example, the opening of the device. So for example, lens, if lens is bigger, that's good, right? And similarly, how about wavelength? Will larger wavelength gonna give you better resolution or smaller wavelength? Should you be using sound wave or light wave or even shorter wavelength, for example, X-rays? Okay, how do you decide? How do you know? So that's what this diffraction and interference helps us to decide. So what happens? When we are trying to look something, we are looking at the light reflected from that object, right? So now those objects acts like a light source. And the light source that's coming out from there, they're gonna be interfering with each other, right? So what that means, so if you can see those maxima and minima and separate them, that means they are interfering, that's a mixing together. Two sources are mixing together and you cannot tell if they are two sources or one source. But if they are not mixing enough, so yes, there are gonna be some mixing up, but if we are in the range where they haven't mixed much, then we can say, oh, there are two separate sources. So that's what this condition is about, okay? So for example, one cell, another cell, or if you are using, let's say, a telescope to look at stars. And when we look with our just naked eye, what happens? It may look like a one star. But when you use better telescope, you can tell, oh, there are more than one star in that one star looking thingy. Okay, so you can resolve those two stars. You can separate them. Okay, you can see the fine details. So that's what it means. So see, this looks like a d sine theta is equal to m times lambda thingy, right? The m has a fixed value for this equation. The guy came up with this criteria, okay? And this d, or you can write a, so a gonna be the opening, okay? A gonna be the opening, and lambda gonna be the wavelength of the source you are using, light source, okay? If we are using our regular light, we know what the wavelength is, right? So now, what is this delta theta? If we want to resolve this, if we want to see them as a distinct, what has to be the case for the delta theta? Is delta theta, should the delta theta be bigger or smaller? If it is bigger, then we can, even bigger, then we can say, oh, they are separate, far from each other. But when the angle becomes smaller and smaller, at a certain point, they're gonna look like just one, okay? So for better resolution, what do we want? Larger angle. That's what we want, larger angle. So how do we get larger angle? So for that, it's gonna see, the wavelength gonna determine that, A gonna determine that. And wavelength, we know what kind of telescope it is. If it is using light, we can use wavelength of light. If it is using something different, there are radio waves in a radio telescope, okay? That uses a radio wave that has very long wavelength. But those radio telescope has also very large diameter, means A is really large for them, okay? So let's rearrange this. So again, it's going to be easier to see if I were to rewrite this something like this, A times delta theta, assuming the theta is going to be still small, right, is greater or equal to that number some constant 1.22 times wavelength, right? So delta theta is going to be 1.22 lambda over A. So now what happens? If your instrument can think, okay, even the very small angle as a big angle, if it can show it as a big angle, that means it is resolving it, okay? So what happens? We want to be able to see even very small angle possible. That's what we want, okay? So what that means, if we want that, then what happens? To make the angle small angle visible, fine details, wavelength has to be smaller. Smaller wavelength gives you finer detail or gives you better resolution. And size of the telescope or the lens you are using, okay, has to be bigger. So this one has to be bigger so that we can see fine detail. So that we can see the fine detail. Smallest the angle we can see, that means it has bigger resolution. So that's how it works. And we can get that condition by using this knowledge of interference in diffraction, okay? So here there is this radio telescope. I recently read in the news that it has become kind of dysfunctional. Something went wrong, okay? But it's been there. And see, it has a very large diameter, 305 meter. 1 meter is about the size of your length of your desk. That's about 1 meter, right? So it is 305 meter. So if you are trying to make glass lenses that big, it's not going to be possible. But with the radio wave, you can just make a wire net. Wire net acts like a lens, okay, for the radio wave. So you can make this very large, okay. And there is this frequency in megahertz, okay. At a frequency of that, what is the angle between two stars that can barely be resolved? So we want to find that delta theta thingy here, right? So same condition, we are looking for delta theta. So we know this information. Do we know wavelength? So for that, we need to use this formula. See, the radio wave is also electromagnetic wave. So that means it has a fixed speed, c, which is this value. Divide that by frequency, you get wavelength. So that is the wavelength, okay? And if you solve this, you're gonna get wavelength in the order of meter, okay? So it has long wavelength. Radio wave can have wavelength going from few centimeters to few kilometers. There is wide range of radio frequency. Okay, so that's what we used, and that gives us that many radians. And from there, you can find the angle, okay? So 0.23 degree. Now, how much is 0.23 degree? So for that, if you want to have some idea, do you guys remember this protractor thingy? Right? It has like reading from 0 to 180 degree. So that means each of those are 1 degree, right? So I don't know if I have it, okay? I have somewhere, but it's not here. So I'm pretty sure you guys remember that, right? So now it is 0.23 degrees, means 1/4 of a degree. So that's a small angle, okay? And that's the angle made by the stars, okay, waves coming out from the stars. So those stars are big, very far. Farther they are, smaller the angle becomes. So we cannot resolve them, okay? So what happens is that when we use telescope, then they can resolve it. And probably you may have heard about electron microscope. So in that case, the electron are used as a light rather than light itself. Light has very long wavelength compared to the wave generated by the electron. So wavelength becomes very small. So because of that, electron microscope can see the atom. They can resolve the atoms in the matter. They are called electron microscope not because they can see electron. No, we don't have any device with which we can see electron. Those are very tiny, tiny animals. Oh, are they animals? No. Okay. So they are very small thingy. Okay. So we cannot, but we can see the atoms. And one atom, and then there is cloud of another atom, and so on. So that's what we can see. So we can count how many atoms are there using the electron microscope. And I think we'll talk about that one when we talk about matter wave, when we say, okay, matter also acts like a wave. Okay. Oh, looks like it's already past the break time. So let's take break, and probably I think there is some clicker questions. Okay, so I'll make them ready. Looks like I haven't opened the clicker yet. I see there is a link in the chat. So thank you, Cameron. So what do you think? Did you find any news? Oh, it breaks. Second cable breaks. It's on the airline right there. Okay, welcome back, folks. So we learned how, what interference and diffraction are, and how do we translate that in equation so that we can properly describe the phenomenon we see, like a bright spot, not so bright spot, during the interference and diffraction. We learned that. And when we started talking about this chapter, I showed you very colorful soap bubble, right? So soap bubble seems colorful sometimes when you look from a certain angle. Okay. Similarly, when there is some thin film of water sitting on, sorry, thin film of oil sitting on the water layer, what happens? And if you look from a certain angle, you may be able to see some color, that the film appears to be color. So there is no colors. There are no colors, added color. It's because of this interference and diffraction phenomenon. Okay, so diffraction is also a kind of interference. So we can just talk in terms of interference. So now, how does that happens? How, how do we describe that, that those color in the thin films? How do we describe that? So we can use all the knowledge we learned so far in this chapter, and we need a couple of things before we actually start describing that, okay? So let's have a little patience here. So what happens is there are no distinct light coherent source, and we learn that we need coherent source. So what happens is in these thin films, the light reflected from the upper boundary, upper layer, and the lower boundary, those two light interfere with each other, and that produces the interference. And when we are looking directly from that angle, in that case, we may be able to see it, okay? So now we need to know what happens. Remember, the interference, constructive or destructive, depends on the phase. So now we need to know what happens to the phase when light reflects from certain boundary. Does the phase remain same or it changes? So we have to have that knowledge before we can predict what kind of interference pattern we can see, okay? So before we actually describe about the interference pattern, first let's learn how does a wave reflects from different kind of boundary, okay? So here it says hard boundary, fixed. So in terms of light waves, hard means medium with higher refractive index. Refractive index, we denoted that by n, lowercase n. So higher refractive index means it's like a higher boundary. So what does it mean? So if light is going from air to the water, water has higher refractive index than air, means in that layer, that boundary, water acts like a hard boundary. Air is not so hard boundary, okay? And so now for that, we can look at just the string, how the string bounces, okay? So for example, if you tie a string fixed at one point and then give some, energy there to produce wave, right? And then what happens? The wave on the string travels and hits that fixed boundary and gets reflected. Does the phase remain same? What does that mean? If it was going before hitting, right before hitting the boundary, if there was a crest, when it returns right after hitting, does it return as a crest or as a trough? If it is returning as a trough, so it went from crest to trough, reversal of phase, 180-degree change, opposite phase. But if it returns back, same phase, as a crest, hits as a crest and comes back as a crest, that means there is no phase change, okay? So for the hard boundary, let's see what happens. So there is this animation here. Oops, what happened? Okay, so crest, trough. right? It hits as a crest, comes back as a trough. So that means there is 180-degree phase change. So what that means? That means when light hits the water surface or glass surface that has higher refractive index than the air, when light reflects back from that surface, what happens? Its phase reverses. So we need to keep that in mind. So now, not fixed or soft boundary. So soft boundary means when light, let's say, coming out from water to the air, what happens? Does the phase change? So it acts like a not fixed boundary, means this node here is not tied, is flexible to move. As the wave arrives, what happens? It moves. And because of that, it makes difference. Let's watch. What's your prediction? Is it reversing or not? It's not, right? So from soft boundary, it does not reverse. Another thing is the frequency doesn't change, okay? Frequency of wave remains same. Another thing, when it passes from one boundary, one medium to another medium, that means when there is a refraction, what happens? There is no phase change. So phase changes only when it bounces back or reflects from hard boundary. Just keep that in mind, okay? And that's gonna be good for us. So now here is a question. So is your clicker ready? Oh, what happened to my clicker? I thought oops. I thought I signed up in my clicker. Yeah, forgot to start the class. Okay. Okay, sorry about that. Hopefully now we can get to the class through the clicker. I'll give you half minute to do that. And while doing that, you can also read this question. And you have now a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it closes. Okay, so let's see what we got here. So mostly yes, and that is correct answer. We saw in the fixed boundary what happened? It reversed. Okay, so there was change in phase. It is actually 180-degree change in phase. Okay, so that's one question, and I have series of questions like this. So now it's in between 1 and 3. 1 and 3. 30 seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So no is the correct answer. So in the transmission, there is no phase change. Only hard boundary phase change. Okay. Now this is 3 and 4, between 3 and 4. 3 and 4. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So we got S. So what's happening here? There is oil. Oil has a higher refractive index than water. So water is a soft boundary for oil. If it was coming from the air, then yes, that would be hard boundary. But it's coming from the oil, which has higher refractive index. So it is soft boundary. So for the soft boundary, what happens? There is no phase change, folks. Yeah, sorry, you missed in this one here. Okay. Now between 3 and 5. And 30 seconds. And 5 more seconds. 5, 4, 3, 2, 1. Okay, so it's 3 and 5. So what's happening? There is no reflection. It's a transmission, right? Refraction. In refraction, there is no phase change. So it looks like B is the correct answer in this case. We went kind of half and half here. Okay. And now 4 and 6. 4 and 6. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1. And it closes. Okay, let's see what we got here. So no. So it is transmission or refraction, right? So no is the correct answer in this case. Okay. Maybe I should make one more question. 1 and 6. Okay. So see what happened? It went all the way here. So basically 6 is 1. one went all through all those process and coming back here, getting out. Okay. So what do you think? So again, 1 and 6, 30 seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what happened here. Maybe B is correct answer. Can somebody help me? Why B is correct answer?
I said B is the correct answer because from 1 to 3, it's a transmission, so there's no phase change. And then from 3 to 4, it's reflecting off a soft boundary, so there's no phase change. And then from 4 to 6, it's also a refraction, so there's no phase change.
So it must be same, no change. Excellent. Oh, nice explanation. Great. I'm liking this question here, so I'll make one more question before I move on, okay? Between 2 and 6. Oh, sorry. 2 and 6. 30 seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Huh, hey. So now can I get help?
I said it did change because from 1 to 2, it's a reflection off of a hard boundary, so it changes phases, but from 1 to 6, it didn't change phases. So 2 and 6 would be different.
So it was 180 with respect to this, right? And it was just that, means it is 0. So between these, there is 180-degree change. Yeah. So yes, that is correct answer. Thank you again for the explanation. So now we are ready to explain when or how we get, we see this, the color in the thin films, okay? So 2 possibilities there. One, from the boundaries, and we talked about that, right? And we also talked about if there is path difference. For example, when the path difference is exactly one wavelength, then what's going to happen? No phase change, right? And if it is half, then there's going to be opposite. Okay, so that's two things, right? So let's suppose there is oil, there is water, just like we are seeing here. Okay. In this case, we have a bit mixture of material in the air, right? So there is water and this soap thingy there floating on top of that. That is a bit tricky situation, but this one is easier to see, right? So what's happening there? There is oil, and let's say thickness of the oil is T, okay? And there is water, and refractive index of oil is larger than water, and the air has refractive index smaller than both of them, right? So now, let's suppose we are looking from the air, right? So there is water, there is thin film of oil, and we are standing on the air and watching. So what happens? Light goes from air, right? Goes from air to the oil film. So what happens? It can reflect from there. Part of it gets reflected. And we know there is going to be 180-degree phase change with respect to this one, right? And part of the light can pass through the thin film of oil. So that means refraction there. Oh, there is 180. Oh, I drew that nicely. Okay. And there, no change. And reflection, no change, right? And that means remains just like this. No change. So there is no change and there is change. So just because of this boundary thingy, there is 180-degree phase change. But what happens now? It traveled here and then came back. So it traveled, or let's say the path difference is T plus T. And remember, you may say, okay, it looks like larger than T. Yeah, you are right. Theoretically, it's going to be larger, but practically, thin film we are talking about, right? So how large it can be. So we can simply say, okay, T and T. So path difference is going to be 2 times T. So we need to take account of this and that. So now, this one we can tell, okay, by just looking at what boundary it went through. Now, for the thickness dependence, we need to use the formula. And let's look at the situation, exact same situation, okay? So now, it says, it gives you a thickness and says whether it's going to be constructive interference for the reflection at normal incidence. So normal incidence means like you are watching directly from the top, let's say. So light is going like that and coming back like that, okay? So in other words, the angle involved is very small, okay? So let me draw this. So there is air, so that's how it's going, right? Oil gets in there, no phase change. And then what happens? From there, the reflected one, what happens? It reflects. Oh, this one doesn't have change, but the reflected one. So this is transmitted one and this is reflected one. So this one has no change because it's on the same side, right? But it is on the opposite side. So it's because of the just reflection, right? So that's what doing. So now this one, so now this is this, okay? So it's I'm just drawing here, but that's just reflecting from that point there. So what happens? It arrives to the same page, okay? So this reflected and this reflected that we're going to be looking at when we are looking at the thin film. We're going to be looking at this one and that one. And what's happening? If the thickness wasn't playing any role, we would see, oh, they are coming out of phase. That means it's going to be destructive, right? Out of phase means destructive. This hump canceling this hump because they are in opposite direction, okay? But there is path difference. Now, let's suppose we want to see the constructive interference. Then what has to happen? This one, when it travels this and that, it has to come back like, it has to come back just like that one. So R1 and R2 have to have same phase for constructive interference, and that's what we want. And we want that thickness, okay? We want that thickness to do that. That path difference, thickness gives the path difference, and we want that to do it, okay? So that means we want this thickness to invert the phase of this 2. So this R2 without thickness is this, and with thickness we want this. So that means there is phase reversal. So thickness and phase, how are they related? So I'm coming back there, okay? So we want this. So how are they related with the thickness? Oh, thickness was T there. I wrote D here. So it's the same thing, okay? Don't get confused, please. So that's D is T. That's how we wrote the formula. Formula has a D in it, so I'm writing this, but that D is the thickness in this case. So now, see, the question said constructive, right? And this condition is for the destructive. So why am I using destructive condition to get constructive interference? Any idea? No idea? I'm pretty sure you guys have some idea. Feel free to share it. And remember, don't be afraid to get wrong. Okay? So the destructive is phase flip. And here we want phase flip from the original. Remember, our R2 was like this. Without thickness, R2 was like this. But we want R3 kind of situation, phase flipped. So how do we get phase flip? By using the destructive condition, okay? So that's where I see a lot of students make mistake. The question asks constructive situation. When do you get constructive situation? And it may seem like, oh, constructive is this. That's the formula for constructive, right? But remember, to get constructive where phase is already flipped because of the path difference, because of the reflection at the boundaries, we need to flip that back so that it comes to the same phase. So we are flipping there. So this equation is for flip. and we are looking to flip here. So that's why we are using it, okay? So that's why we are using this. And remember, now this wavelength is, so this path difference is when the light is traveling in the well, inside the well. So that has to be the wavelength of the light when it travels in the well. So what happens is when light travels from goes from one medium to another medium, like if the material has a higher refractive index, what does it mean? It means it slows down. That means its wavelength change. Frequency does not change, but wavelength change, okay? So because of the wavelength change, there is change in speed. So light, yeah, speed is fixed, but it is fixed in one medium. When it goes from one medium to another medium, it's not fixed, speed change, okay? So anyway, that change occurs because of the wavelength change. So it's like when you are just walking on a nice road, you can walk with longer steps, let's say, and suddenly you get into some sort of mud or let's say sand. What happens? Your steps become shorter. Wavelength becomes shorter now, okay? And that translates into slower speed. So you're going to be walking slower on the sand compared to the road. That is very true if you are running, actually, okay? So in walking, you may be able to adjust the pace once you go to the sand, right? But if you are already running at full speed, let's say, and you enter into the sand, your speed gonna be less, smaller. And while doing that, what happens? Your steps are not that far. It's not going that far. They become shorter. That means reduction in wavelength, okay? So that's what happens here for the light as well. Okay, so we are almost there. So now what we need to do is, usually wavelength of light in air, that's what we know. We may be given just wavelength in air, not in oil. So we need to find wavelength in air. How do we do that? Because by using the refractive index. Remember, refractive index and wavelength, they are related. How? Refractive index is the ratio of speed in the medium over vacuum. And, oh, no, other way around. Okay, so C F times lambda. So if F is not changing, for different refractive index means different wavelength, inversely related. So we can use this, okay? So that's what I'm doing. N is C over B, and oil is C over B oil, and B, and we can do that for the air as well. And I can divide one by another one. N oil, and air means this divided by this. So C over B oil, whole thing divided by C over V air. Fraction of fraction, I can go and flip and make it multiplication, right? So standard mathematical technique there. So C cancels, leaving us V air over V oil. So that's what you see there, okay? Okay. So now we need wavelength. So let's write that in terms of wavelength. Wavelength speed is frequency times wavelength. And since frequency does not change, we can cancel that, okay? So that's how wavelengths at two different media are related. Wavelength of light in two different media, that's how they are related, okay? And since the refractive index of air is very close to 1, we can use that as a 1. So that means we can simply say refractive index oil is lambda in air over n oil. So when wavelength of a certain light is given, it's given for the air. So when you find that in the table or in the internet, that's what you find. Okay, just divide that by refractive index of oil. That gives you wavelength in the oil. So it shortens by the same proportion. Okay, so that's what we proved. So we're doing a lot of things here. Okay, we're not just solving a problem, but we are doing a lot of things here. Okay. Whew. So yes, so that's the general equation we can write. So now with that, we can ready to get the thickness there. Let's see. So that's going to be the equation now. Okay. So since we want wavelength, what wavelength going to give? And remember, when we say light, light has 7 color mixture. And thin film, we are looking at color, means we need to look at each of those colors, right? And so here, what we want to do is, okay, what value of M gonna give you what wavelength, and since the thickness is already given and refractive index of oil is known, so lambda air simply depends on M. Everything else is constant. So we can make a table. Okay, we can make a table here for different M's. What happens? We get wavelength. And for this, we need to kind of look for what color has a what wavelength. Okay, so for example, wavelength of light, for example, blue light is around 0.4 micrometer. It has the shortest wavelength. And wavelength of red light is around 0.7 micrometer. So only these are the visible light. Only in that range they are visible. Any other higher frequencies or wavelength, not visible. Okay, we cannot see that. Our eye cannot see that. So any color we are seeing is because of the wavelength in this range. Now, if I look at here, this one has wavelength very close to the blue, bit larger than the blue. So after blue, it goes kind of towards the, I think, greenish. Okay, so it's kind of blue-green kind of color you are seeing. So M is equal to 2 gives you that. Okay, so it's the second order fringe you are looking at when you are looking at that color film of you know, with that thickness, given thickness. So that's what it means. Okay, so now, yes, of course, in the test, I'm not going to be giving you this long problem, but see, we learned how to find wavelength. For example, when there is different refractive index, right? So you should be able to do that. And you should be able to tell whether they are going to be flipped or not. What formula to use, those kind of thing. Yes, that's the kind of question I ask. Okay. So now, what happens? Let's say sometimes when we have a thin film like this, and if you change the thickness of the film, what happens? This interference pattern changes. Okay, so you can change that by changing the thickness. So what it means is it is thickness dependent. Okay, so now you may be using this principle when you are using, you know, wearing that glass. The glass, coating on the glass uses that principle. Let's take a look here. Okay, here, without coating, you may get this kind of glare. Okay, but with the coating, correct thickness of coating, you can make such a way that one that's reflected from inside and outside of the glass, such a way that they go through the destructive interference. Okay, so you can calculate that thickness necessary and make, you know, coat your glass with that thickness. Okay, and so that way you don't get this kind of glare, but nice something like this. Okay, so that's the application in our real life. You see that? And of course, you can find many applications. This is just one example. Oh, looks like I went a little over our time. Sorry about that. And I'm totally one class behind, folks. Okay, I'll see you guys. Oh, it's Wednesday already. I'll see you on Monday.
Thank you.
Thank you.